All right. Thank you, Professor Barr, for the invitation to speak today, and thanks all for coming. Okay, so we will talk about Bayes' formula, what Sherlock Holmes, self-driving cars, and TB testing have in common. So an outline of the talk is the following. So first, I will explain the role of Bayes' formula in a major branch of statistics called Bayesian statistics, right? And that's ultimately tied to a concept called reallocation of gradability. So that's the first section here. And after that, we discuss some history of the formula, and then I'll throw the formula at you. You know, we're gonna look at the formula itself, and then we're gonna see how to apply that formula to solve a problem, and then we're going to look at some modern applications of the formula, okay? So that's the goal. So let's start with, by the way, actually before, we start, I have a disclaimer to make here. I'm not a trained or practicing statistician. When I was in college, I majored in pure mathematics, and I only took one statistics class, and that is under threat of my undergraduate advisor that, if I don't take the class, then I'm not graduate. So I wasn't very fond of the subject, Fast forward many years later, I was a faculty at Lone Star North Harris, and I got a chance to work with many honor students. Somehow none of them seems to be interested in the kind of pure mathematics that I'm interested in, and then their projects always come down to analyzing some data and use statistics and all of that, so I kind of come to have to learn it to work with them, and it's kind of grown on me a little bit here. And so I start to appreciate the power of the subject, But saying that is that so that you can take what I'm about to say here with a certain amount of skepticism, right? This is not the perspective of something who practicing statistics, or not even the perspective of someone who actually thinks statistically. I don't think statistically, whether it's from the frequentist point of view or from the Bayesian point of view. The reason I'm drawn to mathematics is the deterministic nature of the subject, right? So just a disclaimer there, right? Okay. So let's go ahead and get started here. So, as I mentioned, Bayes' formula play a major role in a branch of statistics called Bayesian inference. So there's only two major branches in statistics, frequentist and Bayesian, right? And Bayes' formula play a major role in Bayesian inference. There's pretty much just two principles, main principle of Bayesian inference, and we're going to talk about the first principle here. So the first principle of Bayesian inference, I think it can be explained pretty succinctly from a quote by Sherlock Holmes, the main character of the novel of the same name by Sir Arthur Conan Doyle. And so the quote is from Sherlock Holmes to his sidekick, Dr. Watson, and he said, "How often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth?" So that's the quotes there. We're going to see what he means here in a moment, in an example, right? So here's an example. So imagine that you wake up one day, right? You're ready for work. You go out and you take a look at the sidewalk, and you see that there's water there. So you see some outcome. You see something, right? And so probably, the first question in mind is, what happened, right? Probably you start thinking about the cause. What causes this, right? So there could be a lot of things that cause this. And so, for example, you start to think about, some possibilities here. Maybe there was a, big rain last night. So I'll call it cause A, right? Or maybe, it's some early garden irrigation and they overdo it or something. That's cause B. Or maybe it's just someone walked by and spilled a drink or something. I'll call that cause C. And finally, something a little bit more serious, like a broken sewage pipe or something. I call it cause D. So let's say that, there's four things that come to your mind here that could cause the outcome that you observe, right? All right? And so the first principle of Bayesian inference, in more precise language, is that Bayesian inference is reallocation of gradability across possibilities. All right. So what do we mean? What do we mean by that? If you think about this, using a Bayesian mind, then probably in your mind, this is a picture that coming up here. So at first, without thinking anything, you have 4 possible causes for the outcome. And then let's say I don't know anything, I don't have any evidence, I'll just think about the causes for now. So this is called the prior belief here. And for this simple example, we're just going to assume that everything is equally likely. So you have 4 possibilities. If all of them are equally likely, each one of them, going to have about a quarter of the chance happening, right? So that's 25%. So you can see the vertical axis here is kind of like, you can call it gradability level or you can call it probability. But all 4 of them at first have equal chance of happening, and that's about 25%, 0.25, yeah? And so you start with that, and then you go and you start gathering some evidence, right? So maybe you go around and you see that, the wetness is kind of localized. You don't see anything else, anywhere else, your neighbor or any other parts of the sidewalk is wet, right? So probably it's not going to be big rain last night. So you can eliminate one of the causes there. And so once you eliminate that, then you can update the level of gradability of the other causes. So right now, you only have 4 possible, or 3 probable causes, and then assuming again that they're equally likely, so each one of them should have about 33-something% chance of happening, right? So that is called the posterior belief there. You get the posterior belief by updating your prior belief with some evidence that you gather. Now this posterior belief here would be the prior belief in the next stage. So let's say you go out and you gather some more evidence, right? You look around and you see, the grass may not be wet, so it's probably not going to be irrigation. And so you can probably eliminate, cause B there, the irrigation of the garden. And so now that you have 2 causes, and again, assuming that are equally likely, that each one of them probably have 50% chance of happening, right? And so you continue to update the prior belief to another posterior belief here. And then finally, you go around, you don't see any cups or any, bottles or anything like that, and so it's probably leave you with the last causes here, a broken sewer pipe or something. And so if you think about it in a Bayesian way, what you do is you start with some prior belief and you go and you gather evidence and you continue to update that belief there. All right, so that's that's the first principle of Bayesian inference, and that was summarized in that quote that I had at the beginning there. Now, so what does Bayes' formula, what does it do exactly in this context? So the idea of the formula is that it gives the mathematical relation between the prior allocation of gradability and the posterior reallocation of gradability conditional on the data that you have. So what does it mean here? As you go from the prior here to the posterior, Bayes' formula is a very precise mathematical formula that tells you how to update this level of gradability for the causes there. So it's a formula, you plug it in, and then you will be able to update the level of gradability based on the evidence that you gather, right? So that's what the formula will do, okay? All right. So before we get to the formula and how it does that, let me just tell you a little bit of history about this formula here, all right? As with any major formula, people don't just wake up one day and decide, hey, I'm going to write out this formula, and then they're going to print it in textbook for you to learn, right? It has a history, people thinking about some problems related to that, and same with this formula here. So before we go to Bayes' formula, if you go a few years back, so this is the 18th century, and there's a philosopher named David Hume. So in the 18th century, Hume started to argue that causes and effects are discoverable not by reason, but by experience. In other words, we can never be certain about the cause of a given effect, said Hume, right? And so his argument here was quite unsettling for Christianity, which is the dominant religion in Europe at that time, because to Christianity, God was known as the first cause of everything, right? And so they found this argument pretty unsettling. His argument meant that we can never deal with absolute cause, rather we must make do with probable causes, and it's kind of undermine a core belief of Christianity there, all right? And so at this time in the story then comes our heroes, Thomas Bayes. And so Bayes was born in 1701 to a Presbyterian minister, Joshua Bayes. He studied theology at the University of Edinburgh. And then he was ordained as a minister of the Presbyterian Church by his father, and then he worked in his father's ministry in London. All right. So around the year of 1734, he kind of moved to a coastal town near London, very beautiful place. I didn't include a name here and then forgot about a name, but it's a nice place. And then, you know, very relaxing place near the beach and something like that. And so, you know, when you look at the ocean, what better thing to think about than to think about mathematics, right? So after he moved there, he started to think about how to apply mathematics, specifically probability theory, to the study of cause and effect, all right? And then this is his famous thought experiments that started Bayesian statistics. So I want you to imagine that this is like a huge billiard table, right? And so Bayes would, you know, stand here and have his back, you know, against the table, so you can't see anything on the table, all right? You can't see anything on the table. Now, on the table, there's a white ball, the cue ball. So the cue ball is located somewhere on the table, right? This line here, so you can do it in 2 dimensions, but for now, let's just say it's 1 dimension. Let's just say that the white ball is located somewhere on this line, and we want to find out where the line is. So if you think about this as 0 and this 1, and the line is probably at about the location 0.3 horizontally. So the white ball is located here, all right? And the Bayes don't see anything on the table. So what one of his friends does is that the friend will randomly throw a red ball on the table. After the ball settles, then the friend would just report to Bayes the location of the red ball relative to the white ball. So for example, if you throw a ball and it lands here, then his friend would tell him that the red ball lands to the right side of the white ball. And so Bayes' brilliant idea is that once he knows that information, he would basically make a guess. And the guess is that if the red ball is on the right side of the white ball, then probably the white ball should be somewhere on the left of the table. You know, if you think about in the middle here is 0.5, then the left ball probably going to be at a location a little bit lower than 0.5. And then he have his friend continue to do that process. Just keep throwing the red ball and report the location of red ball relative to the white ball to him. And so for example, let's say that you throw a bunch of red balls and you throw like 20 of them, 19 of which land to the right side of the white ball, and he's probably pretty confident that the white ball is probably to the far left of the table. Right? He continued to update it. You know, if it's on the left side, then he probably moved the line to the right a little bit. But if on the right side, he moved it to the left a little bit. And eventually, the more evidence he has, the better the guess is going to be. Right? So just to summarize this, as more data, the result of the throws were collected, then Bayes would become more and more confident of the cue ball's position. And you know, he had gone from an effect, which is the result of the throws, back to a probable cause, which is the cue ball's position. And so that idea seems to be a pretty revolutionary idea at that time, and it was discussed by members of the Royal Society. The Royal Society is kind of like the equivalent of the National Academy of Science here in the United States, or the Institute of Advanced Study. You know, so it was discussed by people in that society. Bayes himself, though, didn't seem to be very fond of the idea. So he wrote it down in his journal, but he never published his work, okay? And then when he died, his family would ask his young friend, Richard Bayes, to examine his mathematical papers. Richard Bayes is a very well-known man, you know, even in the United States. I think he's friend with Hamilton and, Benjamin Franklin, right? Is that right? Yeah, and so his family asked, you know, Richard Bayes to examine his paper, and Bayes, who himself is a Welsh minister of the Presbyterian Church, somehow he found Bayes' work on cause and effect, and he somehow saw it as a way to counter Hume's attack on causation. You know, I have no interest of going into that because this is a math talk, but you know, if you read the book, there's books written about it, how he would use Bayes' idea to counter Hume's attack on causation. You know, I recommend that. I haven't finished the book yet, so you know, didn't quite understand his argument, but feel free to find out. In any case, he spent 2 years working on a manuscript, and he correcting some mistakes and adding some references, and then finally he sent it to the Royal Society, which eventually published the manuscript. And the manuscript entitled An Essay Towards Solving a Problem in the Doctrine of Chances. It was published in 1763, 2 years after Bayes' death. And then in that, it contains the famous Bayes formula there. All right, so let's take a look at what the formula looked like, okay? This is the formula. This is probably the simplest version of the formula that I could find. If you look at the textbook that we use here, when we teach statistics, then you're certainly not going to see this formula. But the formula say this. The formula say that the prior odds for a certain hypothesis multiplied by, this is the multiply sign, multiplied by the likelihood ratio, going to be equals to the posterior odds for the hypothesis. So again, if you want to find the posterior odds for some hypothesis, the formula say that all you need to do is to multiply two things, the prior odds of the hypothesis and the likelihood ratio. All right? It looks pretty simple, right? We're going to explain the components in the formula in a moment, but it's just a multiplication problem. If you think about the kind of thing you learn in math, and this is relatively simple, right? If you think about like quadratic formula, there's square roots and fraction and all of that, there's none of that here, right? Okay, and yet Bayes' name is attached to every single book in statistics. So let's think about the components in this formula here. So there's a couple of things that we need to clarify here. So what is the odds here? And then what is the likelihood ratio? You know about posterior and prior from the example that we saw, right? All right, so, okay, so let's talk about the concept of odds. So the odds for an event, by definition, is going to be the probability of it happening divided by the probability of it not happening. So that's called the odds. So what do we mean by that? Let's look at some example here. So imagine that you have a standard 52 card deck, all right? And then you don't see the cards. You just randomly draw a card from the deck, right? Randomly draw one card from the deck. The odds that you draw an ace from that card deck at random would be 4 out of 48. 4 out of 48. Why is that? 4 is the possible outcomes that are in favor of drawing an ace, right? There's 4 aces here. So there's 4 out of 52 chance that you're going to get an ace, right? On the other hand, there's 48 unfavorable outcomes, right? 48 are, the cards that are not an ace, so there's 48 unfavorable outcomes. So it's 4 favorable versus 48 unfavorable, yeah? So 4 is the chance, 4 is the outcome that you get it, and 48 is the outcome that you don't get it. So it's 4 out of 48, and then you can simplify this fraction to 1/12. Does that make sense? Yeah? If you want to think about it in a simpler way, you can also think about it like this. I mean, there's 13 ranks in a card deck, right? There's A's, K, Q, J, 2, 3, 4, 5, whatever, right? There's 13 ranks. The ace is one of the rank, and there's 12 ranks that are not an ace. So if you draw it, so the chance, the favorable outcome is 1 versus 12. So that's 1 out of 12 there. You can think about it that way as well. Yeah? We good with the concept of odds? All right. Another example, just to make it a little bit more clear, is that the odds for drawing a heart is 13 out of 39 because there are 13 favorable outcomes and 39 unfavorable outcomes. And if you simplify it as 1 out of 3, you can also think about it like there's 4 switches, and one of the switches is the heart, and then the other 3 are not the heart. So it's 1 out of 3. So that's the concept of the odds. Okay? All right, so that's one component in Bayes' formula. The other components of Bayes' formula is a little bit more complicated here. It's the likelihood ratio. And so by definition here, the likelihood ratio compares the relative support provided by a piece of evidence for two competing hypotheses. I'm going to call those hypotheses A and B. So the likelihood ratio is equal to the probability of evidence, assuming that A is true, divided by the probability of evidence, assuming that B is true. So that's the formula for the likelihood ratio. All right, so let's go ahead and clarify that by an example here. So, think about a situation where this is criminal prosecution, right? The prosecutor brought out some evidence, a piece of evidence, which is a DNA sample that matches a suspect's DNA profile. So that's the evidence, okay? There's two competing hypotheses here. Hypothesis A is that the suspect is guilty. Hypothesis B is that the suspect is not guilty, okay? Now, The probability of the evidence, the probability that you get the DNA sample that matches the suspect DNA, assuming that the suspect is guilty, is 100%. Because, if the guy did it and you get the DNA, then it's 100% that it's going to be his DNA. So that's 100%, that's 1, right? 100% is 100 over 100, that's 1. On the other hand, the probability of evidence, assuming that hypothesis B is true, which is the guy is not guilty, is probably pretty low. So if the guy is not guilty, somebody else did it, right? The chance that his DNA match with somebody else's DNA is probably low. I would just make up a number here and I say 1 in 1 million. So the probability of the evidence, assuming he's not guilty, is 1 in a million. And so to calculate the likelihood ratio, you would just take the probability of evidence assuming A, which is 1, divided by the probability of evidence assuming B, which is 1 out of a million. And then you know from algebra that if you take 1 and you divide by a fraction, you take the reciprocal of the fraction, right? And the reciprocal of 1 out of a million is a million here. That is the likelihood ratio. And so what this is saying is that the observed evidence is a million times more likely if hypothesis A is true than if hypothesis B is true. So the fact that you have this evidence here is a million times more likely if the suspect is guilty versus than if he's not guilty. So that's the likelihood ratio. Okay? So those are the two components in Bayes' formula here, the priors and the likelihood ratio. Okay. Any question at this point? All right, so, let's see how this is actually applied in a situation here. So a well-known situation where this is applied is in tuberculosis testing, TB testing, a dangerous disease, right? So, let's say that a researcher devised a new and inexpensive skin test for detecting TB, right? So there's a skin test that they come up with for detecting TB. The test claimed to be 95% accurate. So what does it mean? It means that 95% of people with TB and 95% of people without TB will be correctly classified. So if you imagine that 100 people, right, all of them have TB, they come in and they take the test is going to give you 95 positive results, and the test is going to give you 5 negative results. It missed 5 people who have TB, but it correctly identified 95 people who have TB. If 100 people with TB come in and take the test. If 100 people without TB come in and take the test, then the test is going to give you 95 negative results and then 5 positive results. So those 5 people, they don't have any TB, and yet the test say that they do, right? So that's 95% accurate with people with TB and without TB, yeah? All right, and so the question we want to consider here would be, we assume that in this population here, just 1 out of 50 people would have TB, so it's a pretty rare disease. The question we want to consider here is that if somebody random in the population come in and take the test, and the test return a positive result, what is the actual probability that they are truly having TB? So that's the question we want to consider, and we're going to use Bayes' formula, to answer this question here. Okay? Any question on the setup of the situation here? All right, so let's see how, Bayes' formula is used to answer this question here. Okay, so, this is a learner-centered institution, right? So I'm going to try to practice being learner-centered. We're going to go through a sequence of questions, and then I'm going to ask you something, and then, we see if we can answer that, okay? So in order to apply, Bayes' formula, remember we need to calculate the priors and the likelihood and all of that, right? So before we even do that, let's just identify the components here. We need some evidence, and we need a hypothesis we're interested in, and we need a competing hypothesis so that we can calculate the likelihood ratio, right? So the first question I have for you here is that, what would be the evidence in this case, and what would be hypothesis A, something that we're interested in, and what would be hypothesis B, which is the competing hypothesis? Okay, let's take a moment. What do you think? What would be the evidence here, and what are the two hypotheses here?
Has TB, doesn't have TB?
Those are the two hypotheses. Thank you. What about the evidence here?
95% accurate.
That is more like, the probability there. The evidence is what you gather, right? So
1 in 50 people
what you gather is the test result, right? So you have a positive test result. That's your evidence, right? And then the two competing hypotheses is the person who took the test has TB, and the person, the competing hypothesis is that person doesn't have TB. So that's the setup, yeah? All right, so now once we have that, then we're going to go and calculate the prior. So I think, you know, this is going to relate it to something that you just said there. So who wants to answer this question here? What is the prior odds? The prior odds is the odds for hypothesis A, right? What is the odds that somebody in random have TB? So that's like after they take the test. But this here is prior, like before the evidence, before the test. What's the chance that someone random, you know, what's the odds that someone random in the population? 50-50. I think it's way lower than that, right?
1 to 50.
That's right, 1 to 50. But 1 to 50 is more like a chance. And so the odds would be actually 1 out of 49, right? Yeah, because odds is, you know, favorable. I mean, I probably shouldn't use the word favorable here, but, you know, odds is you have it versus you don't have it, right? You have it, there's 1 person out of 50 people have it, and then 49 out of 50 people who don't have it. So the odds is 1 out of 49. It's, you know, having the disease versus not having the disease. Yeah, so that's the odds, yeah? We good? All right, so now we need the likelihood ratio, which is a little bit more complicated here, so we're probably going to need a little bit more time. So take a few moments to see if you can calculate the likelihood ratio in this case. Remember, the likelihood ratio is the probability of evidence, assuming A is true, divided by the probability of evidence, assuming that B is true. So we're not going to use the 149 until the very end, but the likelihood ratio definitely related to the 0.95 here. Anyone else want to give it a shot? 0.2? Pretty close. It's actually 0.95 over 0.05. And so if you plug that into calculator, it's 19. So where does that come from? Let's think about this. Right? So remember, numerator is the probability of the evidence, assuming that A is true, right? So if you assume that, you know, A is true, you are assuming the person has TB, right? If the person has TB, what is the chance that the test give a positive result? 95%, yeah? Because test is 95% accurate. So that's 0.95 there. We good? And so the denominator is the probability of the evidence, assuming that B is true. So B is true is you assume that the person who took the test don't have the disease, right? Doesn't have the disease. Then the test can still give a small chance of positive, still have a small chance of being positive. That would be 5%, right? Because 95% accurate when, you know, you don't have the disease. So assuming that the evidence is true, then it's 0.05 is the chance that, you know, the test is going to give a positive result. And so you divide those two numbers and you get 19, and that is called the likelihood ratio. So what is the final answer then? What's the answer to what we want to find out here? So you have the prior right here, which is, you know, 1 out of 49. That's the prior odds. And you have a likelihood ratio, which is 19. So what would be the odds that, you know, the person have TB with that evidence of a positive test result? What would you do? What do you do with the priors and the likelihood ratio? Exactly. That's what the formula said. You multiply them. So basically, the final answer is the posterior odds is the prior odds times the likelihood ratio, and that's going to be 1 over 49 times 19, which is 19 out of 49. So this is the odds that the person has the disease, okay, given that the test is positive. Now, if you want to transform this to probability, the chance that the person have the disease. Remember, this means that there's 19 outcomes for which the person have the disease, and this is 49 outcomes for which the person doesn't have the disease. So overall, there's going to be 19 plus 49, which is 68 outcomes, right? Of the 68 outcomes, 19 of them is when the person does have the disease. So if you want to transform it to probability, it's 19 out of 68, which is 28%, okay? And so what happened here is that from a prior odds, from the prior chance of 2%, right? Just 1 out of 50 people have the disease. From a prior chance of 2%, with the evidence of a positive test results, then the chance that person have disease updated into 28%. Still pretty low. That's why, if you want to test for rare disease, the doctor would order, a host of tests rather than just one test. Given that this test seems to be pretty accurate, but, with a positive result and with a rare disease, then it just updates to 28%, right? So that's why you kind of understand why, for rare disease, people don't just do one test. They do a host of tests and other things. All right. So that's an example where Bayes' formula is applied. Okay. Any question on that? All right. Now, before we move on to some, modern applications here, let me just show you how the formula is presented in the textbook that we teach here. This is how the formula is presented in the textbook that we teach. It resembles nothing of the, the idea that, I showed you earlier. But if you look at it a little bit more closely, it's look intimidating, but if you look at it a little bit more closely, this here, think about the H here as the hypothesis, and the E here is the evidence. So this is telling you that the probability of hypothesis given the evidence, that's the posterior, right, is equal to this guy here, P of H here. This is the probability of the hypothesis with no evidence. So that's the priors. And this whole complicated fraction here, essentially that's the likelihood. And so this could be simplified to something that looks like this. So you can think about this is the posterior, and then this is the prior, and then this is the likelihood, and they transform it to probability instead of odds. So it looks a little bit more complicated, but it's essentially say the same thing. You can see the components of the idea in there. Posterior, prior, and then likelihood. Yeah? And so that's, the modern version of Bayes' formula there. Okay? All right. So, okay, so in the last part of the talk here, I'm going to look at some modern applications of the formula. The first, there's a typo here. This is self-driving, not self-pricing. Sorry about that. But the first modern application of Bayes' formula is in an algorithm that is called a Kalman filter. And so Kalman filter is used anytime you try to locate something like the position of your Tesla or the position of other vehicles, that is in the same row with your Tesla. Or you may want to study the movement of a robot through a warehouse, or maybe, the location of airplanes, of drones, or whatever it is that you try to locate something, then likely you're going to use a version of the Kalman filter algorithm. Okay, so let's talk about it a little bit here. This here is the set of formula for the Kalman filter, right? It's pretty complicated, but there's two main steps here. There's the prediction step, and there's the update step, okay? So then, at this point of the talk, I would invite us to lock the door here and stay here for the next 24 to 48 hours to see if we can work out the details of this formula here. Just kidding. We don't need to, basically go into detail of the formula, but all I want you to see here is, where Bayes' formula appears in here, right? So at first, there's something called the mean and the covariance. So think about the mean as the most likely position of your Tesla, right? Where it is. And then the covariance is kind of like measures some sort of uncertainty. So you're going to see a picture of that in a moment, but you can't know the exact position. So you have a most likely position, and then there's some chances to the left, there's some chances to the right, there's some chances in front and in the back or something. So think about this as a measure of some uncertainty. So then at first, you want to use the law of physics and all of that to try to figure out the location of the vehicle with some uncertainty. And then now you're going to gather some evidence, maybe from, a radar or, I don't know, some sensor or something, and then you want to update both the location and your uncertainty of the location. And so if you notice here, this part right here, it appears right here in this formula, and it gets multiplied by something, right? There's some term added to this, but the point is it gets multiplied by something. So this prior here gets multiplied by something, and then it gives you the next location right there. And then see, this uncertainty here, it appears right here, and it also gets multiplied by something, and it gives you the next location. So basically in the update step, Bayes' formula is applied right here. This is kind of like the likelihood ratio multiplied by the prior, and this is the likelihood ratio multiplied by the prior to give you, the updated location. So it's actually incorporated in common filter here. And so if you want to think about a picture of the situation here, just imagine for now this is a one-dimensional situation. This is the current location of your Tesla, right? This peak here, everyone saw this bell-shaped curve, right? You saw that, the normal distribution. And so this is saying that, it's most likely to be right in the middle here. That's the location. And then the width of that bell-shaped curve is kind of like tell you about the uncertainty. The wider it is, the less certain you are about the location, right? So that is measured by something called a variance. But if you have multiple direction, it's called a covariance. So it measures how uncertain you are. The wider it is, the more uncertain you are. Right? And so now you use the law of physics, Newton's law of motion, which are deterministic law, you make a prediction. So this is kind of like the priors right here. So with that prediction, maybe it tells you that you're in the next time period. So right now you're here, in the next minute or so, it tells you that you are there with some sort of uncertainty. And then you read the GPS, you read the sensor, it's kind of the evidence that you gather. So the sensor, the GPS tell you that maybe you're here with certain kind of uncertainties. Then once you have the priors, which is the prediction here, together with the evidence, you would put that together using the common filter algorithm, which is built upon Bayes' formula, and then you got, a better estimate of your location in the next time, right? And then notice that, it's become narrow, which means that you're actually a little bit more certain here, right? So the algorithm actually reduces uncertainty there. It tells you the location with less uncertainty, okay? So that's the idea of a common filter, okay? So that's one application. Another application that I want to mention here is algorithm that is used, for example, in predicting, house price. So, for example, imagine this situation. You like to sell your house, right? And you have a data set that consists of houses, within your zip codes or nearby zip codes that were sold recently, right? And within that data set, you can extract some important features that would affect the sale price. For example, what is the size of the house? What year is it built? How many bedrooms it have? What's the location? Is it near any park or good school or something like that? The image of the house and, all of that, right? So you have all of those in a data set of house that was sold already, right? What you want to do is you want to build a model so that based on that previous data, so that now when you plug in the information that you know about your house, that model can tell you how much your house should be, should sell, right? And so that can be done with something called the BNN algorithm. This is short for Bayesian neural networks. So let me tell you a little bit about the Bayesian neural networks here. All right. So neural networks consist of neurons, the kind of thing we have, in your brain, similar to that. So this is what a single Bayesian neuron looks like. So imagine the input here is kind of like one of the features, maybe, the size of your house or something. That input, you would look at the input for, the data points in the house that were already sold. Right? So let's say that you look at a house that already sold, you saw that there's 4 bedrooms or something, right? And you want to see how that affects the selling price of that house. So you would assign the W here, which is kind of like a weight to that input. So how important it is for you, how important it is in that feature, right? The higher it is, the more important the feature is. You would multiply that input by the weights, and you add some Bayes term here, and you plug it into some function called the activation function. And so what it will give you is an output, which is kind of like the sale price that is predicted by the model, right? So you look at the data point that you have, you put in the input, it gives you the sale price based on the model. And you would actually compare that with the actual sale price. If it really close, it means that your choice of the weight and the bias is pretty good. If it's far away, then you would need to update the choice of the weight and the bias to make it a little bit closer, right? And so guess what's happening when you try to update that based on the evidence? What is used to update that? It's Bayes formula. So you use Bayes formula to kind of update the weight and the bias based on the evidence that you have. And you go through and you look at all the data points in the data set that you already have. That's called the training sets, right? And so if you look at that and then you look at that and you look at all the features, then you put all these neurons together, and it's called a Bayesian neural network. And so you have all those features go through with all the data points in the training set. It's going to continue to update the weights and the bias to make it really good to the points that it worked really well with the training sets. Okay, with the data that you have. And once you build that model, then you can plug in the information about your own house, and it's going to give you a prediction. And you would hope that it gives you a pretty accurate prediction there. And so the whole idea is that you have a training set, you subject it to this calculation so that you can continue to update your model. The process of updating that model, use Bayes formula there. Then to improve the model so that you can use it to make prediction for data that haven't seen before or not in the training sets. So that's the idea of the Bayesian neural networks. All right. So there's 2 points that I like to make before I end this. The first is that the idea of the common filter and the idea of Bayesian neural networks is developed actually a long time ago. It was probably in the 60s or the 70s. So Common developed his idea in the 60s, and when he presented his idea, he faced with a lot of skepticism, right? And eventually it get applied, but in the context of military, federal agency who have the computing power to apply it. It's not until the advance of modern computer that these ideas find widespread applications. Because you can imagine that one of these neurons here, this is some calculation to do. And then if you put a neural network together, it's probably thousands and millions of neurons. And so the calculation the idea was there years ago, but the calculation is pretty much impossible at that time. And with the advance of computer science, then they put it together. And in fact, the idea of Bayesian neural networks is actually one of the things behind the large language models, which is the thing underlying ChatGPT and all of these things that you heard lately. All right. And so it's kind of like a mix between statistics and computer science, okay? So that's one point I want to make. Those two together are going to make useful applications. And then another point I want to make before I end here is that I cannot let the statistician and the computer scientist take all the credit here. Because if you think about what's going on behind the scene here, the neuron and neural network look complicated, but all it does is it takes an input and it processes it somehow and gives you an output, right? Does that remind you of something that you have seen, maybe in your college algebra class? What kind of thing that take inputs and do something with it and then give you an output? Anyone? College algebra? What is that? Huh? Calculator, okay. But like in college algebra, what kind of thing in math that take an input, do something with it, and give you an output? What is it? It starts with an F. It is a function, right? And so the idea of the Bayesian network is that if you try to predict something, you try to come up with an extremely complicated function. So when you put in the input, it gives you an output. That's very complicated, so complicated that you can even write out a formula for it. But every one of these neurons here is really simple function. The activation function here is almost like piecewise. It equals to 1 when something happens, 0 when something happens, -1 when something happens. So you try to build a really complicated function with really simple pieces here. And the question is, how is it even possible, right? How do you know that it's possible to get simple pieces and put together to come up with something close to a complicated function? That idea is based on a theorem in mathematics in the 18th century by a mathematician, German mathematician called Carl Weierstrass. It's called Weierstrass approximation theorem. He proved that no matter how complicated your function is, you can always build it from simple pieces like piecewise and polynomial functions. So the whole reason why it could exist is based on the Weierstrass theorem there, theoretically. All right, so with that, I would end here. Thank you for your time.